3.11 hyperbolic functions. This is probably something a lot of you haven't seen before, but it's very similar to trig functions. So if you remember when you started talking about trig functions, it may have been a little daunting, but just because it's a new type of function. And this is new, but it's kind of like trig functions. So don't fear. So let me show you a graph just to give you the idea of what hyperbolic functions are, and I'll start with some trig functions that we know and are familiar with. You know, all the regular trig functions that we deal with, they're all based on the unit circle. There's a circle with radius 1, and to get them graphically you draw the radius out, and then depending on what the angle is, it determines the height of that right triangle, which is the sine of the angle. And then the bottom leg of that triangle is the cosine, and then you get the tangent function, and then the flips of those, the cotangent, cosecant, secant, etc. Well, the hyperbolic functions, they use the same ideas, except instead of the unit circle, they're all based on what you might call the unit hyperbola. That's why they're hyperbolic functions. So the big idea is now, if you draw your line out to that hyperbola from the origin, and then look at the right triangle that's formed there, the far leg is your sine hyperbolic, written S-I-N-H, and the bottom leg is cosine hyperbolic, or cosine H, C-O-S-H. Of some alpha. So you'll hear me refer to these as sinh and cosh, just as shorthand. I've heard many different pronunciations of them, and I don't think there's maybe one standard. But the idea is that the alpha that you're plugging in is not necessarily the angle here, but rather the area of this, not the triangle part, but the triangle that's cut off by the hyperbola. So, and then negative area would be represented by below the x-axis. But same idea. So one thing to note, that sinh can be negative, right? It's negative here, and it's positive here. But look at the cosh, that is that bottom leg, it never gets less than 1. 1 is the smallest, and then anything else, any other number that we're plugging into those hyperbolic functions, the cosh is going to be greater than 1. So it's always greater than or equal to 1. Okay, so let's get back to the definitions here. So this, look at these two functions here, sinh and cosh. That is how we define them mathematically. So sinh and cosh, both in terms of e to the x power, sinh has a negative, cosh has a positive. So if you need help remembering which is which, just remember if you're subtracting these, sinh has the possibility of being 0 because you're subtracting. Whereas cosh, you're adding two positive numbers. E to the x and 1 over e to the x are both positive numbers. So that can never be 0. So cosh has the positive, sinh has the negative. And then the familiar way you get the other trig functions, we're going to get the same thing for our hyperbolic functions. Notice we're just going to put an h after all of them to indicate this is the hyperbolic function, not the trig function. But tanh, to get tanh, you would take your sinh, which is e to the x minus e to the negative x all over 2, and then that would be over the cosh of x, which is e to the x plus e to the negative x all over 2. And notice if you simplify this, the 2's cancel out, and so tanh of x is really just e to the x minus e to the negative x all over e to the x plus e to the negative x. And then cosech, sech, and cotanh, we get the same way that we would with the trig functions. So here's an application. I won't go through a specific example, but you actually see cosh a lot of times in nature when you see telephone wires draping between telephone poles. If you thought that was parabola, you're close, but not quite right. It's actually formed by a hyperbolic function involving cosh. Okay, so let's look at the derivatives of some of these hyperbolic functions. So let me just write this, given the definition that we know about sinh of x, which is e to the x minus e to the negative x all over 2. I'm going to take the derivative of that. But notice the 2 on the bottom, I could really think of that as a 1/2 constant multiple. So really I'm going to take the derivative of e to the x minus e to the negative x. Oop. Let's see if I can move this. There we go. So I'm really just taking the derivative of e to the x over e to the negative x. All right, but that's easy enough, right? Because we know how to take the derivative of e to the x, first of all. That's just e to the x. And then we want the derivative of e to the negative x, but that's just e to the negative x times so I'm chain ruling this, times the derivative of negative x, which is just -1. So, simplifying that, you get 1/2 e to the x plus e to the negative x. But of course, let me just write this a different way, put the 2 on the bottom, and notice what you have. That's just the definition of cosine hyperbolic, or cosh x. Alright, which shouldn't come as a surprise, because if you remember with trig functions, the derivative of sine was cosine, so now we have the derivative of sinh is cosh. Alright, let's look at derivative of cosh, and you might take a guess at what this is, but let me just run through it really quick, because your guess is not going to be right. Cosh is e to the x plus e to the negative x all over 2. Alright, but again, I'm going to take that 1/2 out, take the derivative of e to the x plus e to the negative x. Alright. Derivative of e to the x, of course, is e to the x, and derivative of e to the negative x is e to the negative x times the derivative of negative x. Chain ruling that, and simplifying, now we get 1/2 e to the x minus e to the negative x, which is just e to the x minus e to the negative x, clarify that, over 2, which of course is sinh of x. So remember, when we took derivative of cosine, we got negative sine, but now when we take the derivative of cosh, we get just positive sinh, no negative. Alright, what if we took a derivative of tanh? Well, I'm going to think of this as just, instead of the full definition with e to the x and e to the negative x, I'm going to think of this as sinh of x and cosh of x. But we're going to have to use the quotient rule here. So that is low cosh of x, d high, but derivative of sinh we just figured out was cosh of x. Alright, minus high sinh of x times derivative of cosh of x. Let me get rid of that. Derivative of cosh x is, of course, sinh. So times sinh of x all over lo squared, which is cosh squared. All right, so let me write this out, simplify it a little bit. Cosh of x squared minus sinh of x squared all over cosh of x squared. Okay, I would like to simplify this, and I could split this up over the negative and call it 1 minus tanh squared. 1 minus tanh squared of x. But let me go another route too. Let me look at this by the definitions. So, at least the numerator. So I'm going to plug the definitions in for the numerator. That is e to the x plus e to the negative x squared. I'm missing my 2. Let me include those in the square. Right, minus e to the x minus e to the negative x over 2 squared. And this is all over cosh of x squared. Okay, well, notice both these fractions are going to be over 4. So really I'm just playing with the tops here when I square them and add them together. So that first fraction becomes e to the 2x plus e to the x e to the minus x, and you get 2 of those, and then e to the minus 2x. And then minus, so that was the first fraction. This is all going to be over 4, and that is all going to be over cosh squared. Okay, so now I'm squaring the second fraction here. That is e to the 2x minus 2 e to the x e to the negative x, and then plus e to the negative 2x. All right, now look at what you can combine, keeping in mind that we are distributing this negative. And also notice that e to the x and e to the negative x, that those exponents add together and give you e to the 0, which is just 1. Let me get rid of those. This one's going to be a positive 2. This is a positive 2, so that'll become 4. What about everything else though? How about the e to the 2x minus e to the 2x? Well, those are going to go away. And then what about e to the negative 2x minus e to the negative 2x? Those are going to go away. So this all comes out to be 4, but notice we've also got a 4 on the bottom. So that is 4 over 4 all over cosh squared of x. So we really have 1 over cosh squared of x. But that, because 1 over cosh is sech, or secant hyperbolic, so that is just sech squared. And that one doesn't come as a surprise because derivative of tangent is secant squared, and now we have derivative of tanh is sech squared. All right, so look at the derivatives of the other ones and see if you can figure out what those are. The other ones being derivative of sech, derivative of cosh, and derivative of cosech. Here's some identities of hyperbolics that are similar but a little different from the from the trig functions, the corresponding trig functions, notice what we just figured out on that last slide was that cosh squared minus sinh squared equals 1, as opposed to the trig functions, which are cosine squared plus sine squared equals 1. So also what we figured out was that 1 minus tanh squared is sech squared. And you can get that by just dividing each of these by cosh squared. Alright, so here are the rest of those derivatives. Derivative of cosech is negative cosech cotanh. Derivative of sech is negative sech tanh. And derivative of cosh, cotangent hyperbolic, I should be a little careful about how I pronounce this one, is cosech squared, negative. So notice where the negatives are compared to where they were on the trig functions. On the trig functions, all the co-functions have negatives. But on hyperbolics, it's not the co-functions, it's the ones that are, I don't know, maybe you would say the not the three standard functions. Okay, let's look at inverse hyperbolic functions really quick. Inverse, when you're trying to find an inverse function, remember, this is back in algebra, you start out by switching the x's and y's. So I'm going to call this my left side, this my right side, and switch the x's and y's, and then we solve for y. So x equals e to the y minus e to the negative y over 2. All right, let's see what we can do with this. I want to solve for y to figure out what the inverse sinh hyperbolic function is. So let me see, maybe first I'll multiply both sides by 2. That'll make it a little easier to look at. Okay, well, we've got that. Maybe next thing I'll do is multiply everything by an e to the y. So I'll do that on both sides. And you get 2x e to the y equals, let's see, distribute that in, you're going to get e to the 2y minus 1. E to the y and e to the negative y cancel out. Alright, let's see, let me solve this for 0, because notice what I have here is a quadratic function equation. So if I move this left side over, I'll have 0 equals e to the 2y minus 2x e to the y minus 1. Alright, let me get a little trickier. If this is a quadratic equation, I could use the quadratic formula here, and then I'd be solving for e to the y. But I think instead what's that other process? Complete the square here. So I'm going to start out by adding 1 to both sides. And let me switch these around because I like working with the left side. Get rid of my little error there. Okay, so if I add 1 to both sides and switch things around, so left side becomes the right side, right becomes left, I get this. E to the 2y minus 2x e to the y equals 1. Now I need to figure out what to add to the left side to complete the square. So if you remember, that is, you take what's in front of the thing you're solving for. So I'm solving for e to the y, and I'm going to take this and you divide by 2 and square it. So if I divide 2x by 2 and square it, I just get x squared. So I am adding, let's squeeze this in here, adding an x squared You have to do it to both sides. All right. But what that lets me do is factor the left side. And I can factor it this way. E to the y minus x squared. So this squared is why we call it completing the square. I added what I needed to so that the left side would be squared. Now the whole reason we're doing this is so that I can go from having 2 e to the y's down to just the 1. Notice I have just the 1 because I need to solve for that. So this is 1 plus x squared. Now I need to square root both sides. E to the y minus x equals square root, and I'm going to skip a detail here. And then I'm going to add x to both sides. So I am here. Don't forget my plus here. 1 plus x squared. Now, I want to solve for y, so I'm going to ln both sides. Alright, so that leaves me with y equals ln x plus square root 1 plus x squared. Alright, so that means if the original function was sinh, that means sinh inverse of x, that's what we solved for, is natural log x plus root 1 plus x squared. Alright, so you can try this with any of the other hyperbolic functions. The process is similar. Here's a little more, a cleaner look at what we just went through. And then here's what you should get if you do it for the sinh, cosh, and tant, if you find their inverse functions. Slight difference here. And notice also what the domain is for these functions. Here's the other three, cosech, sech, and cotanch inverse. And then lastly, because this is calculus, here are the derivatives of those hyperbolic inverse hyperbolic functions. I won't go through the details of how to solve these because once you know what sinh is, you already know how to take once you know what sinh inverse is, for example, you already know how to take the derivative of something like that. Okay, I'm going to leave it there. Try some of the problems that I post and catch me on Discord.